So I want to talk now about the law of cosines. And as promised, this is it's a more annoying formula than the law of sines, but it doesn't have that annoying, we could have like 5 different possible cases that we need to worry about stuff that you get with the law of cosines. So in some ways, this is maybe a little bit more straightforward to actually do the problems. You got to use a more complicated formula. The law of cosines is really a generalization of the Pythagorean theorem in some ways. And the nice thing about it is a generalization of the Pythagorean theorem that works for all triangles. So just like kind of philosophically with the law of sines, the nice thing about the law of sines is sine and cosine, these are defined in terms of the unit circle and in terms of right triangles. But it turns out, as we saw with the law of sines, they tell us things about arbitrary triangles, not just right triangles, but any triangle. Well, the law of cosines shows us how cosine tells us something about any triangle, not just right triangles. So let me draw a triangle here for you, and then we will write down the law of cosines. So this is just some triangle. It is not necessarily a right triangle. And in order to make things a little easier, let's label the sides as A, B, and C. Instead of using A, B, and C lowercase for the angles, I think I'm actually going to use Greek letters, alpha, beta, and gamma. Those are the first 3 Greek letters, or the first 3 letters of the Greek alphabet, I guess I should say. That way we don't have to worry about the difference between capital C and little c. So hopefully you guys are comfortable with using these symbols. Now, what does the law of cosines say? Well, the law of cosines says the following. It says that c squared equals a squared plus b squared minus 2ab cosine gamma. And that's literally what it says. Now notice, this looks an awful lot, the first part of this, if I just ignored this piece, this would be the Pythagorean theorem. But we have this additional piece sitting on there, right? We have this minus 2ab cosine gamma that is sitting on there. And that is sort of a correction for the fact that gamma is not necessarily a right angle. So notice, if gamma is equal to 90 degrees, or pi over 2 radians, then the cosine of 90 degrees is equal to 0. So if this is in fact a right angle, that makes c into the hypotenuse, and then this whole formula simplifies to c squared equals a squared plus b squared, because this term is then being multiplied by 0 and it goes away. So this really is just a generalization of the Pythagorean theorem. One of the nice things about this is that it works for all 3 sides kind of symmetrically, okay? So another way of writing this would be a squared equals b squared plus c squared minus 2bc cosine alpha. And I can also write that b squared equals a squared plus c squared minus 2ac cosine beta. The reason is because I could relabel these however I want to. This is not a special triangle like a right triangle. C is not the hypotenuse anymore. C is just some side of some triangle. It's not anything special. It's not picked out in any way. So if I just relabeled these, well, in the new labeling, I would get one of these formulas. But it doesn't matter how I pick to label this triangle. It's true no matter what. Now, I'm not going to show you the proof of this thing. You can look in book. If you're really interested in the proof, let me know. But I feel like getting to the end of the semester here, I'm not going to clutter up your brain with extra stuff here at this point. So I will leave it to you guys to look into the actual proof yourself, or ask me if you are really, really interested in it. All right, so how do you remember this thing? Well, the way that I remember this is that it is basically the Pythagorean theorem, except you have this correction term, which has a minus 2 on it. And then you take the 2 sides that are on the right-hand side and you multiply by the cosine of the angle which is opposite to whatever this third side is. So remember that this angle is opposite to the third side. If we think of these as our first two sides, and C, or in these next formulas, A or B, are the third side, well, this angle is always the angle which is opposite to this side that's on the left hand of the equation, the left-hand side of the equation. And hopefully that helps you guys remember this. If you come up with some other trick, feel free to let me know, because this is something that you kind of have to just remember, and whatever trick works for you, it's good with me. This is how I kind of try to remember it, but it's up to you. And you do just have to remember that there is a -2 in there. I'm not sure if there's any really good way of doing that, but yeah. So you just have to remember it's -2. The same sides are always on the right-hand side of the equation. So if you have the a squared and b squared, you have the a and the b. If you have the b squared and c squared, you have the b and the c. If you have the a squared and c squared, you have the a and the c. It's always one side appears on the left and the other two appear on the right. And then the angle is the one that is opposite to this third side that came in on the left-hand side of your equation. The nice thing about this, again, is that there's really only going to be one possibility here for any of these types of things. Now, when would you use the law of cosines? Well, it turns out that you use this in the cases of the side angle and side being given. So you know two sides and you know the angle between them. Or when you know all three sides of a triangle. So let's just take a look at how you can use the law of cosines in each of these situations. Let's suppose, first of all, that we want to deal. I'm actually going to start off with a side, side, side example here, just because I feel like doing that one first. So let's suppose that I give you a triangle. I want the whole board for this because it might take me a bit of space. So let's suppose that I give you a triangle and I say that this has a side length of 7 and this has a side length of, let's say, 6. And let's say that this has a side length of 5. And what I would like from you guys is to tell me, what is this angle gamma? Okay, so let's see how we can do that. Well, the way that I'm going to do that is I'm going to say, what I know here in terms of getting an equation that involves this angle gamma is, if I think of this as my side C and this is my side A and B, then I can use the formula C squared equals A squared plus B squared minus 2AB cos gamma. So I first have to pick a form for the law of cosines that is going to involve this angle here. Now I'm just going to plug in all of the given numbers here and figure out what is the cosine of gamma. And once I know the cosine of gamma, I'm pretty much all set. Because then I just have to find cosine inverse gamma. That will automatically be an angle between 0 and 180 degrees. And it will be the angle for the triangle. So unlike the law of sines, I'm not going to have to sit around thinking about, is this a possible triangle? Is it an impossible triangle? Are there more than one triangle that could work here? This is a very, there's no complications that can come into play once you get the problem set up. It's all just a matter of plugging in the numbers. So now that's not to say it's an easy problem, but it's just that you're not going to get into any of those kinds of complications like the law of sines has. Okay, so what do we have in this case? I'm seeing that we have 5 squared is equal to 6 squared plus 7 squared minus 2 times 6 times 7 cosine gamma. Now, at this point, we get 25 is equal to 36 plus 49 minus, let's see, this would be 12 times 7, which is 82, so minus 82 cosine gamma. And then we are going to get, let's see, so 25 minus 36, that would be negative 11 is equal to 49 minus 82 cosine gamma. And then negative 11 minus 49, that would be negative 50, negative 60 equals negative 82 cosine gamma. And at this point, we are going to divide both sides by negative 82. So we get 60 over 82 equals cosine gamma. And we could divide everything here by 2. So we're going to get that the cosine of gamma is equal to 30 over 41. So gamma is equal to cosine inverse of 30 over 41. And if you want that in a decimal approximation, you throw that into a calculator and you're done. Once you have this additional angle, you can find the last two angles either by repeating this process, that's one way to do it, or you now know one of these angles, so you can go ahead and use the law of sines if you prefer to get the other angles. Whatever you feel like doing, okay? Either way will work fine. Now, I do want to say there is one situation in which you can get an impossible triangle with the cosines. So I said there's no real complications, and that's kind of true. But there is one situation with this side, side, side where things could go horribly wrong. And that is if one side is bigger than the sum of the other two sides. So in mathematics, we have the triangle inequality, which says that two sides of a triangle have to add up to bigger than the third side of the triangle. So if that rule were broken, then you would find that when you try to do the law of cosines, you would get an impossible triangle. So let's just really quick run through an example where you get an impossible triangle out of the law of cosines. So let's suppose that we want to find the angle gamma opposite to a side of length 3 if the other two sides are length 1. Well, in this case, we have C equals 3 and A equals B equals 1. Now, I'm not trying to draw this. Normally, I would try to draw it, but as we're going to see, this is an impossible triangle, so yeah, I can't draw one. What you're going to find happens here is you have 3 squared equals 1 squared plus 1 squared minus 2 times 1 cosine gamma. So this tells me that 9 is equal to 2 minus 2 cosine gamma. And this tells me that 7 equals negative 2 cosine gamma. So negative 7/2 is equal to the cosine of gamma. Can anybody see a problem with this? And let me give you a hint here. It is not that this is negative. This being negative is fine. But there is a problem. The problem is that the range of cosine is from -1 to +1. And this is outside that range. So this is impossible. This will always happen in the situation where one side is bigger than the other two sides added together. So what you see here is we've got a side of length 3. The others are length 1. 1 plus 1 is 2. 3 is bigger than 2. So that is impossible. In order to understand kind of why the triangle inequality holds, this is kind of a little bit of a diversion, but I think it's worth taking a minute to talk about, if you think about a triangle with a side of length A and a side of length B, what are all of the triangles that I can make with these two sides? Well, basically, I can say I'm going to keep this side of length B fixed, and I'm going to rotate this angle A around. So the possibilities for triangles that I can form are going to be rotating around like this. So I could get down to like a really small triangle like this, or I could go out to this really obtuse triangle like this that barely even looks like a triangle because my drawing is so messy. But the biggest that I could get is essentially as I get A and B to almost lie in a straight line. And when they lie in a straight line, the total length would be A plus B. So the length of this third side can never be bigger than A plus B. And that's geometrically where this triangle inequality comes from. So in the previous example, the impossibility was that we violated the triangle inequality. We were trying to think about a triangle that is impossible. Now, the good news is that that's really the only kind of complication that you can get with the law of cosines. So there's none of this like two possibilities, three, whatever other craziness that we saw with the law of sines. I almost said three possibilities. There's never three possibilities with the law of sines. 0, 1, or 2. But there's none of that 5 different triangle things. Basically, you either have a valid triangle or the formula breaks because it gives you the cosine is out, the cosine is outside of -1 to 1, and it's impossible. So even though this is a little bit of a complication, I said there are no complications because the complication is only that, the formula breaks. It's not like you have to think about it. You plug it into the formula, and the formula either works, or if it breaks, it's impossible. But there's no worrying about, does this actually work? Does it give us the triangle we're looking for? Again, go back to the last video. We did a bunch of examples and talked about the possibilities that can happen for the law of sines there. Okay, now I said that there was another possibility, and that is when you have the side angle side case. This is not the Special Air Service, for those of you who are familiar with the British Special Forces. This is side angle side. So let's just run through an example of this kind of thing. So let's suppose that I give you a triangle and I say, okay, this triangle has one side of length 3 and one side of length 1. And I also tell you that this angle in the middle here is 75 degrees. And I ask you to find the length of this side here, which we're going to call C. Well, the way that I'm going to do this is I'm going to say, okay, well, C squared is equal to 1 squared plus 3 squared minus 1 times 3 cosine 75 degrees. Okay, so this is just the law of cosines with this information plugged into it. And at this point, everything is actually very, very simple for me. I just get that C squared is equal to 10 minus 3 cosine 75 degrees. That tells me that C is equal to plus or minus the square root of 10 minus 3 cosine 75 degrees. And I want to take the positive root because this is supposed to be a length. It therefore should not be negative. Shouldn't have negative lengths. That doesn't make any sense. You can have negative movement in a direction, but that's not really a length. I mean, it involves a length, but to have a negative number referring to that kind of thing, if you've seen that in physics or whatever, you need a displacement. It's not simply a length, it's a displacement. Lengths have to be bigger than or equal to 0, so we take the positive root. And you just plug this into whatever, you get a calculator, you figure out what is cosine 75 degrees, you figure out what the square root is, and you're done. If we wanted to, we could actually use the, I could write this if I wanted to. This is 1/2 of 150 degrees, so I could use one of the half angle identities to work this out exactly. But I don't actually care to bother doing that, and I'm not going to ask you guys to do that either. Just go ahead, throw it into a calculator. Now, you should know how to do it. I mean, think about how 75 degrees is 1/2 of 150 degrees. So that means, because I know the cosine of 150 degrees, I can actually figure out with the half angle identities, because 150 degrees, that's the same thing as 5 pi over 6. It's one of our special angles where we know sine and cosine. But like I said, just throw this thing into a calculator and be done with it. All right, so that's a quick example of how you can use the law of cosines as well. Now, just really briefly, where does all this stuff come into play? Well, one way that all of this stuff comes into play is when you are thinking about building, let's say, a GPS system. Back in the day, you had to use this stuff to do navigation. When they would navigate on the sea by looking up at the stars and taking measurements and stuff, you had to use all kinds of trig rules for this kind of thing. Similarly, if you were navigating a boat near a coast, you would have to say, look at landmarks on land, where you know where they are, and then you could use the law of sines and the law of cosines to say, okay, we've got these angles, we've got these sides, we can put a triangle on our map and build this thing out and figure out where we are. Turns out, same kind of thing still applies, except instead of things on land, we are now dealing with satellites up in the air, okay? So people who program the satellite systems and the GPS systems and things, they still need to worry about this kind of stuff. So this is really very relevant to us today, at least for those people who are going to be working on navigation, even with satellites. It still involves this kind of stuff. Otherwise, trig functions are really quite useful in a lot of different contexts because, well, trig functions, it turns out they end up describing things other than just triangles and circles and things. And so for the rest of this lecture, I'm going to just really quickly mention a couple of things that the trig functions describe that you might not necessarily expect them to immediately. So one thing that they describe pretty well is the amount of daylight you have per day. It turns out that, roughly speaking, it's not quite exact because of the way that our orbit is not an exact circle around the sun. If you're really interested in this, you can look up astronomy and physics stuff on this. But basically, the hours of daylight in the day follow a trigonometric, a sine curve that has been shifted. So if you're interested in looking at certain, let's say that you're studying animals. I know a lot of you guys are interested in animals. You like vet stuff. That's why you're here, probably. If you're interested in studying animals, one thing that you might be interested in is how does their behavior change based upon the hours of daylight? Well, in order to talk about that, you need to model the hours of daylight in the day, and it turns out that through the year, this follows kind of a sine curve. Another place where these trig functions come into play and why it's so important to understand them is in music. So it turns out any periodic function can be thought of as what's known as a limit of adding together a bunch of trigonometric functions. And sound waves are basically, well, they are a wave pattern. Because they are a wave pattern, they're not necessarily sine waves, but they're some kind of a wave pattern. And it turns out you can write any of those waves to arbitrary accuracy by thinking of adding together a bunch of sine waves. So, how does your digital music work? Well, one way that you can encode music digitally is instead of trying to actually describe the sound wave, now the sound wave itself might be some awful, messy thing that looks like this. If you've ever looked at an actual, like, sound, a thing that measures the sound waves, it often looks like a complete mess. But it turns out you can get that complete mess by simply writing a bunch of sine waves added together. At least you can get it to within arbitrary accuracy. Well, it turns out that as long as you do this to a certain accuracy, the human ear can't distinguish between these sine waves added together and the original real pattern. Because it turns out that all of those differences involve frequencies that are too high for the human ear to pick up. So, the way that you can encode digital music is you literally just break down the incoming sound wave into its component pieces, its sine curve pieces. You write down how big each of those sine curve pieces is, and these are just a sequence of numbers, which is easy to encode in, digitally. And then when you want to play it back, you just do this process in reverse. You add together these sine waves, and you tell the speaker, make that pattern. And this new pattern, it may not be identical to the original pattern, but the differences are smaller than the human ear can detect. So digital music depends upon encoding things using sine waves. The basic idea of encoding things using sine waves is an area of mathematics which is known as Fourier analysis, or Fourier analysis. I'm very bad at pronouncing this name, so Fourier analysis. And it turns out that this Fourier analysis can also be used to study a lot of other stuff in physics and whatnot. Turns out this plays a big role even in, say, quantum mechanics. So all this stuff that you're studying here, it has all sorts of applications that you might not originally think of when you just think, hey, we're studying some stuff about triangles. Well, no, it turns out that this stuff about triangles, yeah, it comes from that, but it turns out that it describes fundamental things in our universe in really interesting ways. All right, so that was kind of just a where do you go from here with trig stuff. If you go on to take Calc 2, you will see more than you ever wanted to of other applications of trig functions that you can use where, again, you wouldn't expect trig functions to come up in these situations, but it turns out, hey, you can use trig functions to make this a lot easier on yourself, and so you do. All right, so we are going to end there. This is kind of my last recorded lecture. So if you guys have questions for me, please let me know. You can come to my office hours, you can email me, and we can set up a time to meet, or whatever works for you guys. I hope that you have had a reasonably good semester despite all of the disruption with Corona and everything, but whatever ends up happening with you guys, I wish you guys all the best in your future endeavors, and I have enjoyed teaching you guys, so I hope that, I know a lot of people don't really like mathematics, but I hope that this class has been at least not too painful for you guys, and maybe even it's been fun at times. Anyway, good luck on all of your final exams and everything, and I will talk to you guys later.